So last time we kind of in the halfway, to complete the genetic solver. So let us continue. And because later on you need to implement the particular encoded GA, right? So in this moment, we probably like to provide more utility function that can be shared or can be reused in your derived class. So if we come back to our library, again, make it as the startup project. So look into our genetic GA solver. And I think we needed to check the data structure that I had planned before. The data structure should be I think should be the best way. For you guys, because you need to implement the GA. So if you have a good data structure design, and that will help you, carry out the rest of the design and make sure your GA can work correctly. So, okay, last time we talked about, okay, this is a diagram or a data structure. So basically we have this kind of design. So so far the business solution, the dimension is fixed, right? Once the solver is instantiated. So because of the length is the number of gene or number of variable. So we are not going to reinitialize. But in reset property, in reset function, user might change the population size, right? So if the population size change, we need to reallocate the memory for this data structure, chromosomes, objective, fitness, and indices. And also select the chromosome and select the objectives. This data structure will be reset once user click on the reset button. So let us quickly see what is that for. So suppose right now we have a problem, right? So we have a job assignment problem. So by default, your GA have a default setting. For example, population size 10, crossover rate 0.8, right? So user click on reset. So during the reset, you need to instantiate memory, allocate memory for those variables, right? Because right now user saying that, well, he like to employ 10 solution agent, 10 chromosome to do the GA evolution, right? So it's 10. And 0.8 is a new, probably user might change that value to 0.5. So this parameter can be changed before the GA evolution. So user needs to click on reset, and then after reset, he can start one iteration to do the GA evolution. So remember that in reset, we need to reallocate memory for this variable. And during the structure, we kind of keep reusing this indices array, because that will help us to, for example, do crossover, do mutation, do selection. So we will allocate that memory once in the reset. We are not going to repeatedly allocate memory within your function. So from now on, you need to keep that in mind. Within the function, any function, if that function is involved in GA evolution, not just GA, for example, the endocolonial optimization for the next meta-heuristic algorithm, particle swarm optimization. Because our meta-heuristic algorithm, it is a kind of evolution algorithm. So the same operation will be repeatedly called, repeatedly executed. So if you have any new statement within that function, it will use up all your memory. So if you need some scrap memory to do some calculation, you need to allocate that memory once before the GA, before the evolution. So don't write any new statement within your function, and don't use list. That is a dynamic list. That object has been defined in the dynamic framework. Don't use that, because that will use up memory. Because your function will be repeatedly called probably 10,000 times, and that will use up all your memory. So you need to carefully design your data structure, which will be used during your operation. So right now here, so we kind of define our data structure right here. This part will be reallocated once in reset function. From now on, we keep using that this data structure to help us to do to do the evolution. So the first time we use it is that we use that to carry out the so-called crossover operation, right? So how can we use it? Well, the idea is that, excuse me. So if you are dealing with the binary GA, so definitely your crossover rate should be so-called gene-based, not chromosome-based. So in that case, your so-called mutation rate should be smaller. It should not reach, probably not reach 0.2. What else? So by default, right now, by default is gene number based, not population size based, so 0.05, right? So we kind of provide this kind of option. So we have mutation enumeration, right? Let me see. Yeah, we have mutation mode. So gene number based or population size based. If it is population based size, the rate should the mutation rate should be the same as the crossover rate. So if the rate is 0.8, that means for 10 population size, so 8 parent should be subject to mutation operation like that. So in our genetic permutation perform mutation operation. So we need to bypass these two kind of cases, right? So we need to switch, maybe if anyway, maybe just use switch in case there is a different kind of problem or not. If mutation type, we call it type, right, equal gene number base. For gene number base, it's a little bit much more complicated than the population base. So population base, probably you can do it in a similar way like we deal with the crossover, right? So it's a genetic operation. We are not going to call it private. Never mind, probably we leave private there. Later if we need to open it, so we will specify the probably protected stuff unprotected. Perform crossover, so it's done, right? All right, so gene base. So what should we do with the gene base? The idea is that we keep reusing the data structure we have. Okay, so how can we take advantage of this memory usage? Selected the chromosome, this data structure will be used later on when we do the selection operation. But here we can take advantage of using this memory, this variable, for us to do the so-called gene-based mutation. So suppose. Right now, since right now we know for these cases we have suppose we have a job, right? So this is a gene, and right now population size 10. Oops. So population size 10. So totally there are 80 genes, right? 80 genes. So the first thing is that we need to know how many genes will be mutated. I mean, if we are using gene-based mutation. So it's simple, right now, 80 times 0.05. So in that case, you will get 4 genes will be mutated, right? 8, 10, 4 genes will be mutated. So then you will arbitrarily let the random number identify the gene location for you. So the gene location starts from 0 right here, up to 79, right? So you will ask the random number generator to randomly select 4 positions. So probably this position has been selected. this place also has been selected. Another one is here, another one is here. So we need to identify the location first. And then what I suggest that we take advantage of this variable. In this moment, this data will be used to let us identify the location of the mutated gene. So once you know this place, we can make this check too. Okay, suppose this is the cases that you encountered right now. So even though the 4 gene is about to be mutated, right? But the number of parent might not be exactly equal 4. So in this case, these three parent needed to be mutated. Where? This line, this parent. This is population, original population, right? So we will say that, oh, okay, this guy subject to mutation, this guy subject to mutation, this guy subject to mutation. And which gene will be mutated? Oh, okay, these two. In that case, these two. For this guy, this position, the gene in this position will be mutated. So we keep this information and pass that to the derived class. Again, that is the virtual function. So in your binary gene GA, you need to do this gene-based mutation. To do that will be easier. So, okay, so let us back to this place. All right, so we will have a number of gene, int number of gene, number of mutated gene, number of gene. Remember, we have a variable data. We have a number of crossover children, right? Okay, we need to during the crossover operation, perform crossover operation. Yeah, okay, we have number of crossover children there. So number of mutated gene equal what? Well, I think this is related to gene base, so we have better put in this block. Gene number base, right? So number of mutated gene equal mutation rate times population size times number of gene, right? And since the rate is double, so we kind of truncate the decimal part. So we have integer number right there. All right, great. So we read through the number. Number of gene, I plus plus, right? So we ask randomizer, so our random number generator. Next, what is the upper limit? Upper limit should what? Let me put it for a limit. Okay, move this by. I don't want to waste multiplication, so put a local variable because we need this local variable. Time limit. Okay, next limit. So right now we have value, right? So it's a anti serial position, right? So randomize serial position. So for this example, the first one might appear here. The first one might appear. So that means A 16, 24, 32, 33, maybe 36. So what you get is 36. So we need to identify the index of the gene, and then the index of the location, right? So I have series position, right? So I have parent ID, right? And also have a gene ID, right? So how can you get a parent ID? Parent ID equal what? Series position divided by what? Number of gene, right? So in this case, should what? 36. 36 divided by 8, right? 4 point blah blah blah. So 3 point. So 0, 1, 2, 3, 4. The index of the parent should be 4. So and then we kind of use this selected objective, and then because it's double, right? So in order to identify this guy is selected, we like to mark it as mark this way. So we kind of use this memory as a scrap ball to identify which pattern will be selected, and which gene will be mutated. So that is the idea. So parent ID is divided by 0. And how about the gene ID? You need to use modular operation. This is the modular operation for C# programming language, number of gene. So you know the parent ID, you know the gene ID this moment, right? So, and then, as I say, we temporarily use this memory to record the mutated parent and the mutated gene. So, I've selected the objective. So, selected the objective. It's a double array, right? The parent ID, we kind of set it into a very peculiar constant. It's called double, non-number. So later on I'll check this array. If it is a non-number, okay, this guy will be selected to do the mutation operation. So that is the idea. We use this array to temporarily record this information. And how about the gene? So select the chromosome, parent ID, and the gene ID. And we also set it very double, and then non-number, extreme double. Oh, I'm sorry, because, okay, gosh. It will not do it, right? So it will not work. Sorry about that. Because we do not have a type special here, so I'm not able to do that well. No, that was a mistake. I cannot do that, right? I cannot do that. The only things I can do, now because I do not have a type, so I cannot set it into double and a, and wow. So it will not going to work because we kind of use temporary class right now. So for the binary GA, then this place should be the 0, 1. And I also cannot use this array, right? Okay. All right, so, okay, in order to make it work, so I needed to probably, very troublesome up to this point. Select objects, okay, I use it, so. We might need another, well. Okay, so in that case, we still need that. So maybe we needed to prepare for. I mean, definitely, I think we needed to have an array. Okay, so it's very troublesome. So maybe we needed to allocate again another memory for us to record this kind of information. Okay, fine. All right, so there's no way because it's T, right? So okay, fine. So I will say the bool, and I call it as mutated gene. Mutated gene bool. Okay, so this one will be used anyway for our gene-based crossover operation. So again, we need to reset it during the reset. So you need to know there's still another reset you need to do that. Okay, so here we will have mutated gene, new bool. That should be population size. Just population size will be enough. And then for okay, it's a Boolean array. Bool array. Smaller than number population size. Plus. Mutated gene, the R's row Bool number gene. Okay, so we have this array and it's ready for us to use. So mutated gene. So in that case, we needed to let's say mutated gene. Parent ID, gene ID equal to okay, I'm sorry, I kind of missed it. This should be number of mutated gene, not number of mutated gene, one by one. So we create this index there, and then we use select double number is okay. Oh, probably, well, it's okay. It's kind of weird. Okay, never mind. Let me go back to using the, because that is the original idea I intended to use, but it's not going to work because we can assign the data to this unknown data type, right? So we go back to here. We set this index array. We kind of set this index array into maybe a minimal number because usually index should be positive, right? So not negative, right? So in this case, we put in the int minima value. So in that case, we look through this array. We know that well, if the value is minima value, definitely this pattern will be selected for mutation. Okay, so forget about the usage of these two variables to do the chromosome gene-based mutation. So indices, indices, parent ID equal int minima value. There is no any number, min value. So if it is a mutation, so we need to do some initialization first. Okay, so we will look for int I equal 0, I smaller than number, so population size, I plus indices. H1 we set into 0. Okay, in order to identify which one will be selected for mutation. And also, we need to reset. We need to do some reset. Mutated gene, right? ICE. So another for loop is required for INTJ700 number of gene, J++. So mutated gene I, it's a bool data type, right? So usually they false. So we kind of reinitialize all these indexes and mutated gene. So later on we will mark it as a true. We set into infinity instead of 0. Okay, so make it 0. So once we look through all the mutated gene, then it's about the time we ask the developer class to do the mutation operation. So it's about the time we kind of starting our counting for mutated gene, mutated children, number of mutated children, number of mutated children start from 0. Okay, so we need to look through the index. I start from I from 0, I up to population size, I++. So if indices I equal int mean value, right? It's mean value. So then we know this parent I will be subject to mutation operation. Okay. And I think probably will provide an array. So okay, fine, it's array. Okay, so we will ask that similar to what? Similar to this crossover a pair parent, right? So we call it mutate at parent. And the first one is the parent ID. Parent ID, right? It's parent ID. That will be okay, right? It's parent ID, just parent ID. And probably we just give it that array, int array. Mutated. No, we are coding, right? We are coding this function. This function has not been defined yet, but it's okay. Parent ID, and then mutated gene. I. Actually, not parent ID, just I. So mutated parent, that means the I's parent I need subject because the index very rarely keep the minimum value. So this one, the I's parent I is subject to mutation operation. And how about the gene? Gene has been stored in here, mutated gene, right? Okay, so we pass that array to it. Mutated parent. That's it. I think that's it. All right, so we need to define this function, right? So this we need to define this one. So make the Visual Studio prepare for us. And then I will call it parent ID. Parent ID. Mutated gene. Well, I'm going to call it mutated flag. Actually, it's a flag for me. So I'm not going to do the mutation because I don't know the data type right here. So it should be public. Virtual. So the direct class needed to do the actual mutation operation there, not in the genetic solver. So let's quickly go back to what we have done here. So we determine, in this time, we determine a number of mutated gene, right? So mutation rate time limit. So then we randomly ask, okay, initialize everything right here. And then we just randomize it, randomly select the position of the gene, and then we know the parent ID and know the gene location. So after that, we mark that selected parent in this array, and also we mark the selected gene in this mutated genes array there. So then we can pass that into this mutated parent function. Okay, so let us directly go back to our binary GA. So similarly, we override this crossover pair, right? A pair, right? So in our binary GA, we needed to do override, mutate a parent. Oh, excuse me. We need to assign the child location for it, right? Okay, so during the perform mutation, right? And before doing that, we need to have int start child ID, right? Each parent will be mutated and generate a child, right? So child ID start from where? From population size plus number of crossover children, right? So remember this figure. I mean, in this case, the number of crossover children are 8, parent is 10. So the mutated child start from this position. That's your position should be population size plus the mutation crossover. Okay, so we need to supply another place. So I then child ID mutation. Right. If I equal that, so we do it this way, and then after that we will increment child ID plus, right? Number of mutated children plus. You see, later on we need to know the total number of genes, including the parent and the mutated children and crossover children, right? So we need to update this number of crossover, number of mutated children plus. So let's go back to this function signature. So parent ID, int, child ID, there. Oh. Okay, so later on you need to implement this mutated parent for permutation GA, for real number GA, like that. So here we have parent ID, right? Int, child ID. Okay. So again, we need to implement this algorithm. If it can be finished by one pass, just do it by one pass, okay? So for int, I start from where? Start from 0. I smaller than number of genes, right? I progress. So it is about the time you assign, right? So you can check that if mutated flag, the IC location is true, that means this gene will be mutated, right? Otherwise, it will not be mutated, right? Else, if it is not, then it's so simple. Chromosome, you can directly access the chromosome, right? Chromosome, parent ID, ICE gene, equal what? No, this value will be assigned to the child 1, right? So, chromosome, child 1, ICE gene will directly pick up the parent from the parent. But if it is mutated, all right, so we need to check the parent. So if chromosome parent I equal either way 1 or 0, right? Since you are dealing with the binary G, so it's obvious. So in that case, our chromosome child 1 IS gene set it to what? Mutated, right? Set to 0. Else set it to 1. So because now you have just to 1. Okay, so the idea is that we try to simplify the implementation in the derived class because we like to deal with all these general operation, make it done in the generic solver. So later you will appreciate this kind of object-oriented inheritance mechanism. You can easily implement the rest of different kind of encoding scheme there. Okay, same question about this in this part, mutated parent. So I think probably we have done with this part, mutation, gene number based mutation here. So yeah, right. Okay, so it is almost done here. All right, so you do the rest. It means if it is population based, then definitely it will be similar to the crossover, right? So you randomly select number of mutated parent and mark it on the indexes and do the similar. What do you need? Probably just the index, mark it as minimum value, and you know this guy has been chosen. Okay, so you need to do it by yourself. I'm not going to cover that for you. All right, so we have done with this one, right? We have done with the permutation and the crossover. So about the time perform selection operation. So perform selection operation. All right. Okay, let me go back a little bit to the initialization. In the initialization, right? Initialize population, right? So during the reset, we ask the child class to do the initialized position for us. Then we need to evaluate. Population. So we do it. I mean, so we call the auxiliary function right here in the genetic solver. We are not going to bother that in the derived class. Otherwise, derived class might redo that. So, but in case in last time we do it right here, right? Within this follow, we have finished this part, but we'd like to get the initialization task done in derived class only. So we like to evaluate that. So that means the derived class does not need to bother about this function, about this objective function. So we simply move this task back to the generic solver. So generic solver reset, right? So after initialization, so we for INTI start from 0i up to number or population size, excuse me, population size I++. So we call objective function chromosome I, assign that to objective I. There. So similarly, this is for reset, right? So that means the initial population has been updated. Then similarly, we came back to the perform crossover operation. We added that up. So right now you see we look through number of crossover children. I plus 2, child 1. So we have pair. So in this time we will ask what? Objective is child 1, right? Equal objective function chromosome. child 1. So that means after this function call, derived class has populated the gene value for child 1, child 2. So it's about the time we update the objective value here. Child 2, chromosome child 2. So similarly, for the mutation operation, once we ask the child, right? So mutate a child, then objectively child ID. We invoke this function, objective function, child ID, chromosome. So when we finish the reset initialization, and then we enter the GA evolution. So after we finish the crossover and the mutation operation, objective value has been ready there. So it's about the time we perform selection operation. So genetic operation for selection as well. Do we have that function? I mean, calculate, what we call it. Let me check about the instruction. I have names. Alright, so this part objective function, we have this function, yeah, right here. Set fitness from objectives. Okay, we like to set that as a function. So that the operation create right here, perform selection operation. Set fitness from objective. Capitalize it. Set fitness from objective. So your mission is so simple, right? So because the data-wise, right now we have what? We have objective value calculate, right? So that means in initialization and also crossover operation, objective value has been updated there. So objective value is updated, but not the fitness value. Fitness value always should be the biggest one should be the better one. So if the value of fitness is higher than the other one, then the first chromosome is better than the second one. But objective value, probably your automation is minimization, right? So the objective value, so the best chromosome should be maybe the lowest, even minus, right? So in that case, we are not going to need it. So we need the fitness value, no matter whether you are doing the deterministic selection or stochastic selection, we need to set up the fitness value first. So that the good one receive a big amount of fitness. That is the whole idea. So we are set fitness from objective. This is your mission, right? Check about it, that slide. So we will do it right here. So basically what you need is that we need loops rule for int. I start from 0, right? I start from where? All right, int total equal what? Population size plus number of crossover children plus number of mutated children. This is the total number of chromosomes during this generation, right? So up to total I plus plus. You need to calculate the fitness value. I equal what? I don't know. You need to do that from your basically from your objective values anyway. And probably you need to set up some local value to help you to do that. I'm not going to do that for you. So check about the slide. In here, you need to check whether you are dealing with maximization problem or minimization problem, because the calculation will be different. So and also you probably need to use some user specified minimum amount of fitness for the worst chromosome. At least the worst chromosome receives a survival rate, can receive the minimal survival rate. Doesn't matter whether it is deterministic or stochastic distribution. All right, so you need to do that. So all right, so once we have the finished first, then it's about the time we select, because select operation, right? So we need to choose what? Choose a population size chromosome for parent and children, right, into the next generation. So we use that. We use so in this case, we need to sort. Let me use this example to show you the operation. Okay, so what you need to do is that once you carry, so suppose right now this is objective, maybe this is maybe minus 10, 5, minus 19, 4, 40, 32, anyway, it's kind of number, right? So we evaluate the objective value. We evaluate the objective value of the crossover children mutated object. So it's done right there. So we are about to do the selection operation. So convert to fitness value. So probably it's fitness because if it is a minimization, right? This guy maybe receiving maybe 100. I don't know. Doesn't matter. And this may be 80. This may be 30. 11. 5, 4, and 20, 22, does not matter, it works. 77, and 7, and this guy should be the worst one. So rather maybe the objective value is 100, so it's the largest one, so at least we have 1, minimum value is 1. Okay, so that is the fitness 4. So fitness can be served as the relative probability. So later on, if you set up a relative wheel, then at least this guy has a value, a relatively one have a little bit chance to be selected anyway. So all the fitness values should be the positive value. So it's about the time we choose either deterministic selection or stochastic selection. So these parts of the fitness value will be used if it is stochastic selection. This guy will receive 1. This guy will receive 80s. It's relative amount, so this amount in its survivability. So this is 100. So never mind, you don't need to normalize this as a probability because it is a probability, and definitely the value should be smaller than 1, right? So all these probabilities add up should be equal 1.2. You don't need to do that because if you want to do the stochastic selection, what you need is just a relative amount. You just add them all up. And then the random number choose a value. So another related wheel for stochastic selection, you need to do the coding. And then I will show you how to reach that. Okay. But for this moment, if you are use a select deterministic selection, right? So this one is the highest one, right? Should be 100. So if I can sort this fitness array from the largest one, because if I can sort this array maybe into 100 should be the first one, and 80 second one, and 77, and then probably 60. So I like to sort this fitness value from largest to lowest one, but not just this array. I also need to sort the index, right? So 80s belong to chromosome 0, 100 belong to chromosome 2, chromosome 2, right? 30 belong to chromosome 1. So I need to sort these two array simultaneously, which means that let me use a small example. If I have 80, this is 0. and 30, 1, 100s. The index is 2. 1 is 3, 5 is 4, 4 is 5, 26, 27, 22, 7. So suppose I have these two arrays. This one is for this array. And then I needed to set up this initial index, start from 0 up to 10. Then I will ask the array sort function to sort these two arrays for me based on the value of this first array. And also the second array will be sorted to associate with that value. So in that case, once this function is sorted, then it turned out to be like 102, 102, and 80, 0, 80, 0, 31, 31, 20, excuse me, 22, 22, 7, 26, 11, 3, 5, 4. Excuse me. So anyway, I needed to, once I set up fitness value, and then I reset the initial index start from 0 up to, in this case, up to 23. Then I will ask the array sort function to sort these two arrays for me. So later on, I will get this index array appear here. So in that case, I will select maybe suppose I needed to choose 3 parent. So number 2, number 0, number 1 will be selected anyway. That is the selection for the deterministic selection. For stochastic selection, you need to do that by yourself. Okay, so so in this case, so let us go back. So finish, after finish, then do the selection. If selection type deterministic, else that's your stochastic, right? So even the deterministic is so simple, right? So we will ask what? We will ask, well, never mind. We need to assign for int I start from 0 I up to total I plus plus, and then indexes, because we currently use the indexes right now for the selection. So we need to reset indices item equal I first, and then we ask the array to sort. So this time we will invoke not this one. We need to specify the range, right? So okay. All right, this is the sort function we have to invoke. So the first arrays whose value will be used to sort these two arrays, right? So keys, as you read through the instruction, you will see the meaning. So as I said again, we will invoke. I think that should be the this one, the 6th invocation way. So the first array should be the fitness, and then the second one should be indices. Start index start from 0 up to where? Up to total, right? Okay, so as you can see, start from, we will sort these two array for you, starting from the lowest value up to the highest one. By default, the sort the result is sorting from the lowest one up to the highest one, but not our case, right? Because our fitness array, we prefer the better one is the largest one, right? So after the sort, we need to invoke this array inverse. Reverse or inverse? I can't remember. Reverse. Yeah, reverse. Reverse what? Reverse our indices. And from now on, we don't need to take care about the fitness value anymore because the purpose is done, so we don't need to reverse the fitness. It's not necessary. What we need to reverse is the indexes or the parent IDs. So not just this one. The reverse you also need to start from 0 up to total. Otherwise, it will screw up the value. Okay, so let me show you an example. Let me grab this class again. So let me show you what I have done here. Suppose right now, so initially we ask the array solve these two array for us, right? So probably start from 100 and maybe 90, 80, 70. Oh no, excuse me. What after the sort always start from the lowest one, maybe 1, 2, 10, 50, 60, 61, up to here probably maybe 110. And the index has also been sorted, right? So probably index is 4, 3, 16, 16, maybe 18. Doesn't matter. 100, so 20, excuse me, 100, 0, 8. So after the sort, always start from the lowest one up to the highest one. So we need to reverse, but we don't need to reverse this array. We simply reverse this array because this is the index. Apparently. So that means the number 4, 0, 1, 2, 3, 4, the number 4's index is the best one because the array source always start from the lowest value up to the highest value. So we need to reverse this array back up to this place. This should be total, right? So once we reverse it, that means the 4, 3, 14, 16, maybe it's 18, I don't know, doesn't matter. So we have index, all the index reverse right here. So the worst one should be the, maybe, I don't know, it is 17, 16, 8, 9, doesn't matter at all. So right here. So the deterministic is so simple. Well, just the first 10 parent will be survival. Not just parent. The first 10 chromosomes will be survived to the next generation. So in that case, we look through this array, 4, 1, 2, 3, 4, 4. We copy that to this place, gene-wise copy to here, including its objective value. Because objective value has been evaluated, right? So we move it right here. So 4, and then 3, second one, the 0, 1, 2, 3, 3. Copy all the gene to the second one right here. Again, objective value. And this guy 16, so right here, probably 1, 11, 10, 11, 12, 13, 14, 15, 16, 61, this one. So I'll copy to this place, objective value copy here. So what you are doing is that you need to do the gene-wise copy. Don't just copy the reference. You need to gene-wise copy there. Because later we will overwrite everything back here. So 18, 17, maybe, suppose it's 20, so 20 maybe here. This is 20. It's a mutated child, so copy right here. So after the sort, and after the reverse, then we look through for int, I start from 0, I up to population size, I plus. So right now, the index of selected either its parent or child has been stored in the indexes. So indexes I okay, remember that chromosome. Indexes I. And since we need to do the gene-wise copy, so we need to find the int j start from 0, j small than number of genes, j plus plus, one by one copy from this parent. This is a parent, right? This parent has been chosen, right? Has been selected, and then copied into where? Copied to the selected gene, selected chromosome, selected chromosome. I's, J's. So this part is what I'm saying is that, but not just chromosome-wise. We also need to copy the selected objectively. The I's selected copy from objectives. Indices. Maybe you can, well, maybe you can set up a local value to stand for that, but it's okay in this I. Okay, so gene-wise copy genes from parent and children from selected parent and the children to temporary array, temporary matrix, and doesn't matter. And then after that, gene-wise copy genes back to our population. You may first think about, well, probably not, it's not necessary. Why we needed to do this troublesome job? You need it. Otherwise, it will be overwritten. I mean, if you directly copy these guys right to this place, you will screw up the one which has been selected before. So we moved the selected parent or children to this temporary array, and then we one by one copy that back. Actually, you don't need to do that. Once you are smart enough, you can design a pseudocode, design a logic, carefully arrange your indexes and one by one directly override. But I'm not suggesting you do that. I mean, for this moment. So for this moment, what we are doing is that we copy gene-wise, copy to this place, and then gene-wise copy back to complete the generation, the evolution generation. Okay, so and then chromosome I. So in that case, it will be simple. Chromosome I, J, directly copy from I's selected chromosome. So it will be simple. And not just chromosome, also objective value I will be copied back from selected objective I. Okay. Probably you think about, wow, what should I do here? I mean, for the stochastic selection. So use fitness as relativity for each and do, well, we call it spin, relate can I get the correct spelling? Check that really weird. Spin populate size times, right? To set the first population size. So anyway, I mean, if you look into the deterministic selection, the most important is that you need to determine the selected index, right? So in deterministic selection, it's simple. Right now, we just put it in the indexes, right? We kind of sort the indexes array. So the first population size chromosome will be selected. Similarly, for stochastic, you need to do spinning, rate wheel spinning for population size time. So each time you will pick up the index. So again, we still use this array. We still use this array to record the spinning result. So suppose the first spin, the first spin, because this is the probability, right? So this probability. So each one will have a probability to be selected relative population. So suppose if you shoot a dot on this relative wheel. So okay, check about the index. Okay, so right now it's 5. 5 has been selected. So you put in here. Index is 5. And next spin, you hit again. Maybe it's 6. And hit again, spin again 17. So you kind of stochastically select the index from this from the population, from the parent, and from this parent and children chromosome. So in that case, if you are using stochastic selection, so probably because if the suppose this is the biggest one, so what is the biggest one? Because it is the best chromosome, right? So probably this best one is here. The ID is 13, right? So 13 has a largest probability, right? So you will see 13 may be selected multiple times. It's normal because that is for stochastic selection. So in that case, well, once you have determined this, what you need to just population size selection will be now. You don't need to do select result because only this part will be used to select 5 copy here, 6 copy here, 17 copy here, 13 copy here, 17 copy here. So we keep using this index array to store the index to be survivable into the next generation. All right, so the structure right here is short story. This is deterministic selection. This is stochastic. What we prepare is that index is ready for us to choose. So we copy the chromosome, gene-wise chromosome to this temporary array, and then we copy back. So that finish this selection operation. Okay, I think that's it. I mean, for this population. So can we just take a 5 minutes short break, and then we will back to see how our application can use this library to quickly go through the application of this library. Okay, so let us take a 5 minutes break, and we will be back. Right click on this reference tag, add a reference. As I say, normally if you just have a DLL file, you need to use browsers to locate that DLL file and then click on it. But right now, since the DLL generator is generated from another project, so right now we will select project. So as you can see, besides your targeted project, the second project shall appear here. So we check on this one, FCYNG get GL library. So confirm it. So now since you have included, so you will be able to invoke the class there. All right, so this is your main phone. So main phone wise, you need to design it by yourself. Right here, we kind of probably need to prepare some button. Later on, we hate to design to prepare this button because it's the same, right? Always, if you want to set up a project, use GA to solve your problem, you need to prepare the same button repeatedly. You don't need to do that, right? Right now, we just let this button ready and right in the library, so we can directly. We don't need to repeatedly set up this button. Later on I will show you how to do that. But for this, for now, usually we have what? Reset, right? Reset, and also we will have run one iteration, right? And probably we have another button, run to end. I'm not going to cover the detail about the job assignment problem for you. But right now, I might simply show you the procedure of creating a binary GA for your problem. So I might create, I should say, instantiate at binary GA solver. Okay, so let us go back to the main form. So suppose the main form right now, well, since our family, GSO family is well organized right now. So in main form, right, we will have a generic, so we call it generic GS solver. But you need to spell the type, right? So probably we forget about that. We will have binary GA. Binary GA. Okay. So I'm going my GA solver. So we have not instantiated yet. And during this, when this button is clicked, so when this button is clicked, we can use, we can new it, right? So how will you new it? My GSO will equal what? New. So right, that will invoke the binary GA. So take a look at the explanation. No any explanation came out, right? Binary GA, well, probably that is not the cases. Okay, let us go back to the binary GA constructor right here. Yes, there's no any explanation. So if I type this so-called take comment, well, create binary GA solver. And if I add some explanation right here, the delegate to the objective function, something like that. Okay, you can use the type Chinese. So let me rebuild the library, and then let's go back to our main form. So when you try to invoke this function binary GA, right? There's no any information came out, huh? Okay, I know. So never mind. Let us just compile our application. For even though we did not use the GA, we just have a definition there, declaration there right now. Okay. So what will happen? I mean, since your project invoke, your project reference a library, right? So if we look into the directories, so this is the project directory, your project. Take a look at the bin. Because you are using the DLL, right? So the DLL a copy of DLL will be copied to your, your binary folder right here. So right now, your executable code needed this DLL to run the code. So this DLL will be copied to the binary folder there. But let us go back to this library. It's a project. So let me open the property of that project. This is a library project. So at the end, the output will be a DLL, right? So DLL name is right here. You specify by default. It's the same as your project name. So your DLL is exactly the name here. There's an option here, build. In build, there's an option right here. The output, not just the DLL, I also need to output an XML file. So make this check. And then we recompile, we rebuild these libraries. So take a look at what will be generated in this library bin directory level. So not just DLL, also we have an XML file associated with that DLL. Actually, this XML file serves as the documentation of your class. So once this is done, then let us go back to our project right here. And go to the main phone. So try to new a binary GA, right? Well, weird. I cannot see any intelligent information. Equal new. Oh, okay, right here. Sorry. Create a binary GSO, right? So right now we have document associated with this constructor. So suppose the number of variable, well, I say it's 34. Automation type, minimization, objective function. I need objective function. So I call it simple obj function. I do not have this function already, right? But I need it. Okay, so let me just create this function for me. All right, so we just didn't know the type because we just didn't know this delegation. Delegation asks for a byte array, right, for this binary. So I kind of put it here. And here, I'm not going to solve the problem for you because your job assignment problem is much more, complicated than mine. What I'm saying, what I expected, just 01 will be the highest one. Okay, so if a solution just give me 64111111, then it's the well, because this time I might prefer maximization, maximization. So the purpose for this function is just to return a double, right? So I kind of look for each byte be in a solution. If, well, I just sum it up, will be okay. So I'm simply test a case, an optimization problem. If the GA return means the gene value all has 1, then that's the global optimizer for me. So the function is very simple. Just provide a function which type consistent with that dedicated. That will serve as an objective function. So right now I'm testing the simplest one, just always 1. Okay. All right. So I have the GA solver ready, right? So I can invoke this function too. Reset, right? Reset my GA solver, reset, and then run one iteration, right? So similarly, one iteration, my GA solver run one. Oh, okay, it is not public, so maybe go back to our library. Generic GA solver. Run one iteration. It's public, right? No iteration. Run one iteration. Okay. And then we will run to end. Well, let me just one moment as you run to end. I did not input run to end, so that's it. Just that's it. And usually in user interface, we may need to let the user change the parameter. So we will grab in property grid. So once the GSO is instantiated, then, well, once we create it, property grid 1, selected object equal, we assign with my GSO. So this is the simplest application of our GA library, right? So instantiate and GA solver, binary GA solver. So we have crossover rate only. So you need to define the parameters for the rate. So right now crossover type 1-point cut, 2-point cut, right? N-point cut, mutation rate, population size, fine, everything is okay. Probably I kind of change it into 12. So let us trace the code. So since right now the both projects are in the same solution, so actually you can do the source code debugging. From this project into another project, there's no problem. So let me go back to the initialization, right? So reset, okay, reset right here. So when you click on reset, you see you can here, and 3 times size, population size 12, right? It's newly updated by me, right? So when I ask for 12 chromosome, so chromosome right now new T, you see, new T 3 times. What about the TT is actually a byte. So everything's, so how about the indexes? Index 3 times, right? So after instantiation, all are 0, 36. Mutated gene, it's because we use that to record the gene. So let me go through it. So how about mutated gene? See, 12. Each one has 64 bool. So it uses up quite a lot of memory. So maybe it's not good at all, but wow, excuse me. Skip that. So I need to set a breakpoint here and I start it again. Instantiated with, okay, let me this time change it into 8. Reset. So let me execute this point. So right now our chromosome 8 times 3, right? So we prepared 24 chromosomes there. So let me step into this function, initialize population F11. So it came to the overwritten initialization right here. So initialize population here. So up to this point, chromosome has been memory allocated, right? So we have memory already allocated by the genetic solver. So right now it's about the time we randomly assign 0 and 1 to it. So right here. Okay, so up to this moment, you see the first one, well, schedule. So let me execute to this point. So once we finish the initialized population, as you can see, 0, 1, 0, 1 have been arbitrarily set up. All right. Okay, up to 64. And that should be up to 8th. Up to 7th. So we have one winner there. How about the 8th? No, because that part will be for the crossover children and mutated children, right? Okay, so it's done up to this point. And then we kind of evaluate the objective value for those population, right? Right here. So up to 8, right? So if I hit F11 key, so how about objective function? It's a delegate. So if I hit F11 key, capture your main form, this function. So the first solution, right here, solution 0, 1, 1, 1 there. So actually what I have is a maximization problem. If all the solutions are 1, then that should be the global best. So it is very easy, to set up a very simple automation problem. Ask a GA to run the solve for you. So right now, this objective is what? Okay, let me to this point. Sum 34, 34, 1. So actually 34. So let's keep on going on. Oh, objective value is not initialized. I'm sorry about that. So I ask you to do that. Objective. So okay, in order to run it, we need to make it complete. So chromosome right here, index here, mutation rates. So objective it. Three times. Remember that 3 times size. And I don't know whether we completely initialize the memory for the rest of the variable or not. I'm not sure for that. Okay, let me this time remain 10. So initial population, enter it. So this should be the everything should be initialized up to 10, not 11s. Up to 10. So it's initialized. And objective value 2. So let me run through to this point. So now objective value has been evaluated. Okay, so as you can see, from 0 up to 9, that should be our population, current population. They always have their objective value evaluated, right? So probably 32, 1, 41. So this one will be the best one, right? So far, this is the best one. Okay, so we are done with the reset. So it's about the time we run one iteration. So run one iteration is here. Run one iteration. So step into this function, F11 key. Okay, perform crossover operation, right? Perform crossover. So enter it right here, still in the generic solver. So we try to perform the crossover. So crossover rate 0.8, population size 10. So number of crossover children 8. We want to make sure the number is even, not odd number. Okay, and then we shuffle the index array, right? Population size. So we come to the shuffle right here. So array right now we have 30 element, right? So our index limit is 10. We do not do any shuffling, right? So at the end of this shuffle, the index has been ready there. So start from number of children, I plus father. So father index I actually index did not shuffle, right? So 0 parent chromosome 0, chromosome 1 will serve as father and mother, and then cross over right to the 10s and 11, right? So for the first pair of parent, father is 0, mother is 1. How about child 1? Child 1 is 10. Child 2 is 11, right? So the index is really there. So we ask the derived class to do the crossover. So if F11 key can do here, binary GA, father 0, mother 1, child 1 10, child 2 11. So that's the mission. So we can crossover operator. 1 point cut. Current is 1 point cut, right? So we randomly set a cut point position, 50s. So totally the number of genes is what? 64. So as you can see, chromosome child 1 is 10, 11, right? So before that, take a look at the 10s. Always 0, right? And 11s, always 0. So if we finish this assignment, this crossover assignment, let us check the chromosome 10s again. Yeah, the value has been copied there. And if you look into the detail, you may see, well, part of them came from father, some of them from the mother. So it's done. It's done right here. So come back to this place. So then we evaluate the objective value. So up to this point, objective value is just 0 to 9, right? So it's about the finish of the child 10 and child 11, right? So we evaluate the objective value right here. And then again, we will invoke this function provided in your main form. So let me skip it. Done. So objective 10 is already there. So after the crossover, it's not guaranteed that children is always better than the parent. No, not always, right? So we know that. So then we update the index and for the next pair of crossover. So it's done up to this point. We can check the chromosome. So up to this point, that should be up to 17 because we have 8 children generally, right? 8 crossover children, right? But not for the 18s, right? We were mutated were started from the 18s. So it's done with the crossover operation. Then we step into the mutation operation. Every key again here. So gene-based, gene-based. Number of limit, total number of gene, right? So 640 gene, right? And number of mutated gene crossover, the crossover rate is 0.05. So the target of 32 gene were subjected to mutate operation. Okay, 32. All right. So population size. So we initialize everything. Initialize because we use mutated gene stand for the flag. So kind of everything. So mutated gene are always clean up, open up. And then we randomly select from 0 up to 639. So the first selection serial position 23. 23, right? 23. Then we get the parent ID. So parent ID is 0, 23, because 23 fall in the position in the 0's parent, right? And how about gene ID? That should be 23. So in this parent 0, we set it into minimal value. Mutated gene 32. So the second gene to be mutated position, random number 539. Okay, so we need to check out the parent ID. Parent ID is 8. Gene ID 27. So we set index 30 to measure. So up to this point, as you can see, this is a minimal number, right? So we know parent 0 will be chosen for mutation. Parent A will be chosen for mutation operation. Okay, we use that as a flag. Okay, so after this mutation selection, let us check about the indexes. We keep using index. Well, almost all of them will be mutated. So at most just 10, right? So all of them will be mutated. And how about the gene position? Take a look at the gene position. Some of them have been turned into truths, right? Yeah, there's a true there. Okay, so then we will start from the population size, check whether it is minimal. Yes, the ice is minimal. So we mutate parent 0 and the child ID starting from 18th. And mutation gene is right here. This guy, that should be 0, right? So 0, take a look at 0. So gene 9 will be mutated. Yeah, like that. So objective value, well, I did not trace in. So we finish this mutation. So let me step into, okay, this is the second mutation. So let me hit F11 key. Okay, we came to this place. So we check the mutation flag right here. False, false, false. No mutate. This one will mutate, right? Okay. So normally, no any mutation, just direct copy from parent. Child 1 copy from parent. But some gene, if the gene, the flag is turned on to be true, you need to check whether the parent, what kind of value of the parent, and then change the value into the opposite one. So you can set up a breakpoint, but it's a conditional. So learn this trick, okay? condition, set condition. Parent ID I equal 1. So we set a breakpoint. It's a conditional breakpoint. Then we hit continue. Bingo. Okay, right now I has been up to 23. So in that case, we check whether it is 1, 0. Okay, fine. Number 1. So mutation is working. Right? So let me finish this part. So after mutation, how many number of mutated children? 10. So totally there should be 28 chromosome general, right? And oh, okay, yeah. Also, we have objective value, right? So up to this point, you see, objective value has been already there up to 28. Right. Okay. So because we have 8 crossover, 10 mutated children, so totally actually 28 chromosome participate in the selection. All right. So finish the mutation. So we step into the selection operation right here. Okay, I did not set fitness value, so I'm not going to see any positive result here. Okay, total that should be 28. If it determines selection, well, because fitness values are always okay, it's none. The memory has not been allocated. So, well, I think we will end up right here, and almost everything has been done so far for our genetic soul, but because we need to provide some visual display, right, for during the operation. So that means if you look into the application, the demo application, you will see no matter what the problem is, if you are using GA to solve the problem, the only connection should be that delegate, not objective function only, right? But most of the user interface are related to the GA solver. So GA solver, you need to set up something. So definitely we need to provide some graphics user interface to let users select or change the parameter. So in this version, we did not use the public grid. So definitely we will use public grid to show that. But not just that. If you look into this GA evolution, we also needed to provide a chart to simulate the progress of average objective value and iteration-based objective, and also what the best objective, to let the user knowing the convergency of that GA solver, right? So I think when the class, I will do another video instruction for you. Try to wrap up this graphics user interface with your genetic solver. So that will save us a lot of time. I mean, if you, the idea is that if our library have already provided, okay, let me stop it right here. If our library provide this kind of so-called users control, I mean, including property grid and also including this 3 button and also including this chart for us, well, it will be very useful for the user. User does not need to prepare the button by themselves. We would like to wrap up this useful user interface within the library. So later, if a user like to use the default user interface, they can just provide, you user just prepare a panel, and then you put every user control in this panel for the user. That would be good for the user, and that will make your library much more friendly for the user. So later, I will give you guys a video tab showing how to do that, how to integrate a user interface with your GA library to it. Okay. Okay, so as for the job assignment problem, you need to refer to this demo application, and then if you like, you can prepare this kind of user interface to let you understand what the progress of your problem. So But you don't need to worry about the charting. I will guide you how to do that and then integrate that into the generic solver. So later on in your application, you can directly use that. But for the generic, for the job assembly part, you need to prepare this kind of information to help you understand what is the progress. So once you need it, you add a property in your GA library. Because, for example, you need to access the gene value, right? So probably you will, later on, you will come back to your library here, generic solver, try to provide a property to then your application can access it. So for example, chromosome. You might like to have public T chromosome, right? And then simply provide read only, get. Right, made a mistake. Oh, made a mistake there. Yeah, such kind of public property, you will make it public. So in your main phone, you can pick up the value and then do a formatted printout. But then if you need anything, you come back to the generic solver and then set a public property for you to access it. Okay, well, let us stop right here. So I think the due date will be extended probably for another week, but you should do it as soon as possible. Otherwise, well, anyway, we will have the next assignment soon. That should be, again, it's much more complicated than the binary GA. So start your assignment as soon as possible. Okay. All right, so we'll end up right here.